All right, so we're going to talk about representing functions with power series today. So the first thing I want to talk about is some operations that we can do with power series. We already talked last time about integrating and differentiating power series and how that doesn't change the radius of convergence of the power series, but it can change the interval of convergence. We'll do a little bit with that today as well. So some operations. And I'm going to say we're representing f of x by the sum a sub n x to the n, and we're representing g of x as a sum b sub n x to the n. And these are infinite series. F of k times x, where k is a constant, is the sum a sub n k to the n x to the n. So k is some constant. If we have function of x to some power, that's going to be the sum a sub n x to the n times n. And then we have, we can add or subtract functions by adding or subtracting our coefficients. Yeah.
Since k is constant, why is it k to the n of the first one?
Because it's multiplied, so it's multiplied by x here. So every time you see a k, it's multiplying x. So when you see x, you have to plug in kx for every term. And again, these don't change the radius of convergence, but they may change the interval of convergence. So we have to test our endpoints again. And when you integrate or differentiate your power series, you might have to adjust your index. So if you start with n equals 0, but for example, you differentiate, and then your exponent goes to n minus 1, you don't want to start at n equals negative 1, so you might have to re-index your series. So you want to make sure you're starting with the right index if you differentiate or integrate. So sometimes you have to make a change there. All right, so what we're going to do today is with differentiation, integration, and these operations, we're going to talk about how we can find representations, power series representations for different functions without going through the process of doing the Taylor polynomial, finding all the derivatives and all of that kind of thing. So just a different way of finding power series. The first technique is we're going to talk about geometric power series. And we talked about this briefly at the end of the day on Friday, the end of the lesson on Friday. So the idea here, the big idea is we want to write the function in the form f of x equals a over 1 minus r, where r can be some, I'm going to write r of x. So this could be some function, but we want it to look like the sum of a geometric series. A over 1 minus r is the sum of a geometric series. And then we use this to write it as a geometric series, as a power series. Because if we have this as a sum of an infinite geometric series, then the series is the sum n equals 0 to infinity of a sub n r to the, or a r to the n. And r here happens to be a function of x. So let's look at an example of this. This is a very, very powerful technique, and it's used very commonly. So we want to represent f of x equals 1 over 2 minus x. As a power series. And we're going to say for this one, we're going to center this one at 0. Just to make this example a little easier. So we want this, we want the form a over 1 minus r. So what can we do to this to make it look like this? Divide everything by 2, right? So we're going to say f of x equals 1/2 1 minus x over 2. And now we have a equals 1/2, r equals x over 2. And we can write this as a geometric series, as a power series. So we're going to say that f of x equals 1/2 the sum n equals 0 to infinity of x over 2 to the n. And we could write this as just a kind of a cleaner way to write this. N equals 0 to infinity of x to the n over 2 to the n plus 1. Yeah, I just put the 1/2. It's not better. This is just more. You would more likely see it written this way, the second way, than the first way. This is more common notation. And this converges. If we did our, we know this converges because it's geometric between -2 and 2. So this would be a good representation of 1 over 2 minus x between -2 and 2. For a geometric series, you do not, because we know at the endpoints geometric series diverge. Okay. So that's one nice thing about geometric power series. We don't have to worry about it. We already know that. All right, let's look at another example of this where you have to do a little more manipulation. And then we'll use the next example to build further examples. So we want a power series for 1 over x centered at 1. So what we want here is we want our form to be a over 1 minus r, and we want the series in terms of powers of x minus 1. So we want x minus c. So what we need to do is write 1 over x. We need to do some work to write it as 1 over something x minus 1. So what do we need to, and we need a 1 here. So I'm going to put a 1 there. So what do we need to do here to make this work out? Plus, and I'm going to do, and we want 1 minus r, so I'm going to say minus negative x minus 1. Yeah, so that we had a plus, it's not in this form. For a geometric series, we need 1 minus r. So here a is 1, and r is minus x minus 1. So we can say 1 over x equals the sum n equals 0 to infinity of minus 1, I'll just say minus, sorry, x minus 1 to the n. And you'd usually see this one written as a sum n equals 0 to infinity of minus 1 to the n. Just separate out the alternating part, x minus 1 to the n. And our convergence, we converge, our interval is 0 to 2. All right. So when we want a geometric series representation, sometimes you have to play around with the way the function looks to get it to look like a over 1 minus r. Well, you can do the plus 1, minus 1, divide everything by something, do some various manipulations to get it to look the way you want. All right. Well, now let's build on this. Now we're going to do some of our operations. We want to find a power series for natural log of x centered at 1. Now it would be hard to write ln x to look like a over 1 minus r. But what did we just do? We just found a power series for 1 over x. How are natural log and 1 over x related? And I'm going to put a plus c here. And the reason I'm putting the plus c here is, in this case, when we make these power series, we need to explicitly account for the constant, because we want to make sure our function and our power series agree at, for example, x equals 0 or x equals 1. So sometimes that constant turns out to be 0 and we don't have to worry about it, but sometimes we get a constant leading term to make sure the function and the power series agree at a certain value of x. All right, so let's integrate. So I'm going to say the natural log of x equals, and I'm going to put my constant of integration out front. I need to explicitly account for it. The integral of the sum, n equals 0 to infinity, of minus 1 to the n, x minus 1 to the n, dx. And we can take the summation out of the integral. I'll just tell you that you are allowed to do that as an operation. So we're going to do the sum n equals 0 to infinity. And I'm going to bring the minus 1 to the n out because that doesn't depend on x. And we're going to integrate x minus 1 to the n dx. What's the integral of x minus 1 to the n? X minus 1. What do we do to the power? Add 1 to it. And we're going to divide by the new power, n plus 1. And we have the c here. So that's good. We need the constant. All right. And we need the function to agree at, I'm going to say when x equals 1, natural log of 1 equals 0. So we need the function to agree there. And when I plug in 1 here, I get a 0. X equals 1. So that tells us our constant is 0. So with these kinds of power series, a constant does not necessarily always equal 0. That's why we need to explicitly account for it. All right, so there's our power series for natural log of x. We have the sum, n equals 0 to infinity, of minus 1 to the n, x minus 1 to the n plus 1, over n plus 1. And if we test the endpoints for convergence, we have this one converges on 0, and it includes 2. So we get that endpoint, the second endpoint, when we take that integral. So there's a power series representation for natural log of x. That comes from our geometric power series representation for 1 over x.
Should we just know the power series representation for 1 over x? Is that one special?
It might be, but it's easy to, if you remember how to find the geometric power series, you can remember how to get it. All right, and this, now imagine finding the a Taylor polynomial for natural log of x. Doing all those derivatives, you have 1 over x, and you have all these. So that one wouldn't be too bad. Well, let's look at another example. Let's find a power series for inverse tangent of x, centered at 0. So think about how much work would be involved in finding a Taylor polynomials for inverse tangent of x. Those derivatives are really messy. But let's use something that we already know. And this kind of relates back to a little bit to what we did with our opener, our integral of the day. We know the derivative of inverse tangent of x is 1 over 1 plus x squared. Right? This looks kind of like 1 over a minus r. So I'm going to start by looking at 1 over 1 plus x, because once we know the power series for 1 over 1 plus x, we can square each term, and we'll be set. Well, this is 1 over 1 minus negative x. So this is going to equal the sum n equals 0 to infinity of negative 1 to the n x to the n. So we have a negative 1 to the power. I just pulled that out right away. And so we can say 1 over 1 plus x squared is going to be the sum n equals 0 to infinity of minus 1 to the n, x to the 2n. And the tangent inverse is the integral of 1 over 1 plus x squared dx. So we're going to integrate this, and we'll have a power series representation for inverse tangent. So we're going to say inverse tangent of x equals c plus the integral sum n equals 0 to infinity minus 1 to the n x to the 2n dx, c plus sum n equals 0 to infinity. I'm going to pull this out and we'll integrate all in one step. The integral of x to the 2n dx x to the 2n plus 1 over 2n plus 1. And we know that the inverse tangent of 0 is what? What angle has a tangent of 0?
0.
0. Tangent, inverse tangent of 0 is 0. So C equals 0. In this case again. And we have that our inverse tangent of x is the sum n equals 0 to infinity of minus 1 to the n x to the 2n plus 1 over 2n plus 1. And this is, I'm just going to write a couple of terms. So we get all the odd powers of x without factorials, just odd denominators. And this converges. If we test this, it converges between -1 and 1. Yes?
Do we have to know, like, have all these memorized?
It's good to have some of them memorized. But if you don't have them memorized, now you know how to get them.
So which ones are the ones we were
I'll write down some special series in just a second. But I want to point out for this, so since this converges from -1 to 1, we can say the inverse tangent of 1, which is what? Pi over 4. Pi over 4 equals 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9 minus dot dot dot. Pi over 4, this gives us an approximation for pi. So pi would be approximately 4 times 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9. So we have a nice numerical approximation for pi. Isn't that nice?
Not really, but
It's
All
very
right.
nice. What are you talking about?
So power series, applications of power series. If you don't know how to evaluate a difficult integral, you can substitute a power series representation of the function you're trying to integrate and integrate the power series. So you have an approximation at least to the integral. Power series are used in computation because computers are good at multiplying and adding. Really, they're good at adding. And since multiplication is repeated addition, that helps computers do things easily. And it helps us make relationships. Power series helps us make relationships like this, which become important. You never know when they're important. They become important in other applications. All right. Common power series. One over 1 minus x.
No, it's an in order sequence, like thing of things. A thing of things, Kevin.
So this is a power series for 1 over 1 minus x to the n for x, absolute value of x between for x between -1 and 1. 1 over 1 plus x. And now we know how to find all of these. Minus 1 to the n, x to the n. And again, this is for x less than 1. E to the x. And this one's nice because it converges for all x. Sine x.
Oh.
Oh.
No, you're not, Sam.
You already know all this, Sam.
This is for all x. And here we get, just as a note, odd powers and factorials. And the cosine, sum n equals 0 to infinity. We get the even powers and factorials. And if you can't remember if sine or cosine is the even or odd powers, what I remember is that the sine of 0 has to be 0. And the sine of cosine of 0 has to be 1. And this converges for all x. The natural log of x plus 1
Well, that says odd.
minus 1 to n minus 1, x to the n over n. And then finally, the inverse tangent that we just did. Minus 1 to the n, x to the 2n plus 1 over 2n plus 1. So we have odd powers and just odd denominators for inverse tangent. So the only difference between inverse tangent and sine x is that factorial.
And then we just should know these ones.
I would say definitely e to the x, definitely e to the x. At least be familiar with sine and cosine.
We can memorize all of these.
The other ones you can come up with. All right, questions? Yes.
So the range for the last one.
Oh, sorry. There we go. A couple of the homework problems in this assignment, and I can look once we finish here to tell you which ones, involve recognizing derivatives, functions that are derivatives of each other. So just be aware of that.
Thank you. Make some good fun.
You're straight trash.
Enjoy.
And I'm thinking it's 36 through 40 that rely on recognizing derivatives of functions.